The Feistel process, and really the starting point of modern cryptography, it solves the paired pattern pitfall. This process removes the direct links between inputs and outputs, and it creates an output that is fully random. In this lecture, we are going to cover how this works. So Feistel is a direct answer to the problem that Claude Shannon defined, that we need to remove patterns and linkages. And Feistel began his work around the 1950s. And when he published his solution, his process, he quotes Claude Shannon, and Feistel proposes what he calls confusion and diffusion as the answer that we needed. And this is what Feistel gives us. And it's simply known as the Feistel function. And it only has two ingredients. So one, the shuffle box. So this picture and most others in this lecture are from the paper that Feistel published. This first one, this is very easy. It's sometimes called a permutation box. You can imagine this as a piece of hardware, 15 inputs, 15 outputs, and all this is doing is moving the location of each bit. That's it. And number two, also called a transformation box. So in this example, we have our inputs. This is a 0, corresponds to this 0. This middle 0 corresponds to this middle 0. And then this bottom 1 corresponds to this 1. So this is our input. And we have a 001 as the input, which will transform into a 111. And the key difference is the shuffle box is a one-to-one shift. There is a direct line still between the inputs and the outputs. However, this is a non-linear transformation. This is a break between inputs and outputs. So if you look at the individual binary zeros and ones, we have a total of 24 coming in as inputs and a total of 24 going out as output. So in effect, each output has a 50% chance of being a 1 or a 0. And this is very important. So this 50-50 chance means there are no lines across this box. It is a break. And moreover, the output value, it will depend on our neighbors. So in this example, our top input is 0, and our output we're concerned about is a 1. But if our top input had been different, if it had been a 1, then our middle input would have exited now as a 0. So we're bundled together with our neighbors. I like to think of it as a mixing of neighbors, a mixing of bits, with the net result being output values have a 50-50 chance of 0 or 1. So all said, an individual substitution box has no security to it. So if you know all three outputs, it's just a lookup table to find out what the inputs were. And it's even easier with the shuffle box. And both of these items by themselves have no inherent security, but Feistel combines them by placing them one after another, after another, after another, and we get a much different story. So this is showing an encryption process starting with plain text and ending with ciphertext. And a note here is that this is Feistel's example. He is only showing the impact of this single bit, and he's basically ignoring all the other bits. And this sandwich is how we remove the one-to-one links and the patterns. So now each input link, or each input, is now linked to every single output. So we'll zoom in to see this. And this bit, as it goes into its first substitution box, I'm going to bring in some colored shapes now. It's a tad beyond Feistel's example. Our bit is this red circle. All other bit labels, I'll make them squares. And as they pass through the substitution box, their value on the other side is 50-50. It's going to depend on all three when they go in. And these are just example numbers. Say the bit we're following turns into a 0. its two neighbors turn into a 1. But the point here is that these three output values became intertwined as they passed through this box. And again, I'm expanding now on Feistel's example. When our single bit leaves this box, it's going to go through the permutation box, a shuffle, and it's going to change locations. And when it goes into the next S box, substitution box, this substitution box is a different type of transformation because all subboxes have slightly different designs, slightly different ways to achieve this 50-50 chance of their output values. And so now our single bit now is going through a different type of subbox, and it's going to have new different neighbors when it does so. So in addition to that, the other bits that we're now intertwined with, they are entering new substitution boxes as well, and they will also gain new neighbors when they do this. So, and just here we're just showing three different transformation boxes, but our single bit here has an influence on the inputs for all three of these. So when we go back to the start of the example, our single bit started here, it ends here. As it travels through all the various different types of substitution boxes, it becomes more and more intertwined with the other input bits, and also more and more spreads its influence throughout the process. And in effect, this is what removes this one-to-one link, because now the input is intertwined now with every single output. So in the example Feistel provides, we have our input here. This is our single bit, it's 1, and then we have 14 0 bits that follow that. So this bit, along with two other bits, it enters the substitution box. All three bits exit with a 50-50 chance of being a 0 or 1. And then now we have, in this example, two bits exit with the value of 1. And then we can see how this 50-50 transformation grows and spreads. So I pulled the picture left, and I'm going to artificially adjust this output. But the net effect on each output bit, so this output bit, traveled through many 50-50 substitution boxes, is that when it ends up here, its value is the same as flipping a coin. A coin flip is unpredictable, it's random. Same for this bit value here. And this applies to all the output bits. They are all the culmination of all these 50-50 transformations. And this entire value is now random. And then think outside, going back to our starting bit, think outside this small example. The next bit is also doing this. Its pathway is going to look different, but it's fighting for a totally random number at the output, and so is the bit after that. So every bit is fighting to an output of 50-50 to be random, and random means that there are no patterns. And this is how patterns are removed. And now, through the substitution and through the shuffles, every single bit is related to all other output bits. We no longer have the one-to-one links, and we no longer have any patterns when it comes to our ciphertext, our output. So a critical point here is that all of these boxes we just walked through, these are not secret. This whole process is publicly known. An attacker would know every shuffle, every substitution schedule, all of it. Everything is public knowledge. But it helps to look at this backwards. So if we were an attacker and we were starting here with the ciphertext, the encrypted message, how would we try to walk back through this? Given ciphertext or the encrypted message, how would we walk back through this to get the plain text? So we'd start with the first bit and we'd walk backwards. And it would lead us to a substitution box, as it was one of three exits, and we could figure out the three that went in. Take a step back from that, we would be repeating the process, and we would have to determine the inputs to that. And then this would continue until we've traced back, but we would reach every single input bit, not to mention many different bit overlaps along the way. And there is no tracing back. And this is Feistel's description here, is that this is basically one big complex web. You can also think of it as a big mixing bowl where we have the substitutions and iterations, and this is just mixing all of these bits together. This mixing, the simultaneously, is what simultaneously breaks the one-to-one connection and produces the complete random nature, the no patterns in the output. So if we're an attacker and we have this ciphertext, our only option is to start from all the inputs and compute forward, which is to say our only option is brute force. So, and even in this tiny example, the number of potential inputs, this is the number we would have to do a guess and check on. And there are no logic, there are no pattern shortcuts that we could exploit. And Feistel recommended a more appropriate number. And in the 1970s, this number of attempts to brute force was beyond a doubt a secure size. So in doing so, Feistel gave us really the starting point for electric computer modern cryptography.